In this third video lecture on inequalities, we're going to look at absolute value. Specifically, our objective, we want to solve absolute value inequalities algebraically and graphically. Okay, we know a couple things that are going to help us with this lesson. The first is, we know what absolute value means. Absolute value is the distance a number or an expression is from zero. That is certainly going to come into play here as we look to solve absolute value inequalities. Second, we know what an inequality is. An inequality is a statement involving two expressions that are separated by one of the inequality symbols: less than or equal to, greater than or equal to. Okay, we're going to take this in two parts. We're first going to look at the less than symbols, and then we're going to look at the greater than symbols because they're treated differently with absolute value and how to solve them. Okay, so less than and less than or equal to. So right here. Okay, so when we work with less than and less than or equal to, we get one interval centered on zero. Okay, so what does that mean? How does that look? Here's an example. The absolute value of x is less than 3. Okay, so now the absolute value of x means the distance that x is from 0. And of course, less than 3 must be less than 3. So the absolute value of x is less than 3 means the distance from x to 0 must be less than 3. Let's make a number line. So I've drawn a number line here, and I put 0, 3, and negative 3. Okay, where on the number line is the distance less than 3? Well, anything between 3 and negative 3 is that the distance from any point between these numbers, the distance from that number to 0 is going to be less than 3. If I choose 2.8, that distance from 0 is less than 3. If I choose negative 1.5, that distance from 0 is less than 3. You'll notice, because I'm only using the less than symbol here, I've used the parentheses. I used parenthesis option to indicate 3 is not less than 3 from 0. Okay? So when it's just less than, I don't include 3 or negative 3. So here's the inequality that represents this. And you'll notice it's one interval, so there's just this one inequality. The x is between negative 3 and 3. Okay? Or x greater than negative 3 and less than 3 would be how this is said. Okay, so one interval. And we can solve this one interval. We did that in the previous video lecture because this is a compound inequality because it has three expressions and then of course two inequalities. In general, okay, so let's generalize this. Let's call the constant a. In general, the absolute value of an expression that involves x is less than a translates to or is equivalent to the expression is between negative a and a. Okay, and this you do very similarly to when you say the absolute value of the x expression is less than or equal to a. This translates to the inequality that the algebraic expression, in this case represented by u, is between negative a and a, but also equal to. Okay, we have to include the endpoints in this case. An example should help. Let's take a look at this. We want to solve this, and we want to graph the solution set. Okay, so here's my absolute value inequality. The absolute value of 2x plus 4 is less than or equal to 3. Okay, well, I know that I'm going to wind up with one interval. Okay, the distance from anything this comes up with must be less than or equal to 3 from 0. Okay, so this tells me that to be less than or equal to 3, the absolute value means I'm between negative 3 and 3. So this translates to negative 3 is less than or equal to 2x plus 4 is less than or equal to 3. So being less than a number means as an absolute value being less than a number means you must be between the opposite of it and itself. Okay, so we're here, and now we're fine. Okay, we want to solve this for x, so let's separate the x. Let's get the number out of the way. We do the same thing in this case to all three, what I've called sides, but they're not really sides, all three pieces, or all three expressions. 2x is greater than or equal to negative 7, and less than or equal to negative 1. Okay, divide by 2 to solve for x. Okay, and I'm going to come down here. X is between or equal to. I'm just going to leave them as fractions. Now we know this one is negative 3.5 as a decimal, and this is negative 0.5 as a decimal. But we can just leave them as fractions. Okay? All right, so the solution set. Okay, the solution set. In set notation, all x's such that x is greater than or equal to negative 7 halves and less than or equal to negative 1 half. In interval notation, because it can be equal to, we're going to use brackets. So here is interval notation. Negative 7 halves is the smaller number, so it comes first. Negative 1 half is the larger number, so it comes second, and it looks like that. Graphically, I'm going to draw a number line. Again, I always put a 0 on here. I'll put a 0. You don't need the 0, but I always put 0 on it. Negative 1 half, well, let's ballpark it here. Negative 7 halves. Let's put it over here. Of course, it's to the left of negative 1 half. We can be equal to, I'm going to use the bracket method this time. So I'm going to put brackets here and here because brackets indicate equal to. And then, of course, we shade everything in between. And this is our solution, our solution set. Okay, so anything in between these two or equal to these two should make our original absolute value inequality true. Let's just pick a number. How about negative 2? That's in here. Negative 2 times 2 is negative 4. Negative 4 plus 4 is 0. Got lucky. I wasn't expecting that. The absolute value of 0, of course, is 0, and 0 is definitely less than or equal to 3. So that works. I picked a number inside. Let's take a look at this graphically. Okay? Let's go graphically. So I'm going to be focusing here. I'm going to let's take this away for a second. So graphically, let's do our check graphically. Okay, we're going to let y1 equal the left side, so the absolute value of 2x plus 4, and we're going to let y2 equal 3. And what it says here is I want y1 to be less than or equal to y2. So we want y1 to be less than or equal to y2. And let's see what that region is with our calculator. Okay, turn it on. Let's go to graphing. Oops, I got one more. I got something in my y3. Let's clear out my equations. Okay, Absolute value on the TI-84 is a math function under number. So math number, it's the first one. So I'll press enter for absolute value. I want y1 to be the absolute value. I'm right up here of 2x plus 4. Whoops, let's be in my calculator here. There we go. Let's take a little eraser. All right. There's my y1. And I want y2 to, well, let's graph. Think about it for a second. You probably have seen graphing absolute value before. It graphs in the certain shape of a letter. Can you come up with it? Okay, think about that. Can you come up with what letter absolute value graphs at? I'm going to press graph. Let's see if you're right. Absolute value graphs as a V. Okay, absolute value graphs as a V. So there's the graph of the absolute value of 2x plus 4. Let's go back to y equals, and let's put in 3 as our y2. And we know that y equals 3 is a horizontal line, okay, that crosses the y-axis at 3. And we want to know when is the V, the blue graph, below the horizontal line y equals 3. There we have it. Okay, so when is it below? Well, it's below between here, this point, this intersection, and this intersection. That's the part that shows that it's below the y equals 3 line. Okay, so and it's between these two. Well, those are intersections. Let's calculate those intersections. Okay, so I'm going to do the one on the left first. I'm going to go near to it. There's my first curve, my second curve, and check it. I got negative 3.5, which you can see right down here. And we have negative 3.5 right here, which we also called negative 7/2. Now let's check the right intersection point. So the upper limit, I'll go to second calc, intersect. And this time I want to move my cursor closer to that side so my calculator knows where to look. There's my first curve, my second curve, and then I'm pressing enter again, and then I'll press guess. And this is telling me right here, it's x is equal to negative 0.5, negative 1/2, and that's what we have right here. And again, because we have the equals, we know we need either brackets or we need a closed circle, closed endpoints to indicate that negative 7/2 and negative 1/2 are also part of the solution set. They also make this inequality true. Okay, let's take a look at the other half of inequalities, the greater than and the greater than or equal to half. A little bit different. Okay? Now, so with greater than and greater than or equal to, we get two separate intervals. Okay? So when we were doing less than, we wound up with one interval, but it was a compound interval. Go back to here again, you'll take a look. We wound up here with one interval for less than, but it was a compound interval. Okay? With greater than, we wind up with two intervals, but they're not going to be compound. Okay, let's see why that is. The absolute value of x greater than 3. What that means is the distance that x is from 0, absolute value, must be greater than 3. Okay, well where on the number line are numbers that for which the distance from 0 is greater than 3? Well, the positive side's easy. 4, 5, 6, 7, 8, 9, 10, those are all greater than 3 away from 0. The negative side's a little bit more intuitive, a little bit more difficult to think about. Negative 4, negative 5, negative 6, negative 7, the distance from those numbers, the distance of those numbers from 0 is also greater than 3. Okay? So you can see, well, we have two things here. We have answers that go to the right and answers that go to the left, which is what results in this. All x's that are less than negative 3 and all x's that are greater than 3. So we're going to wind up with two inequalities, 1, 2. Notice in this case, because it's just greater than, I chose to use the open circle on the 3 and negative 3 as opposed to the parenthesis. Either one is fine. You see both. That's why I'm using both. Okay? So in general, when you have a greater than, so the expression, the expression involving x is the absolute value of that expression is greater than the number, you wind up with 2. Obviously, the positive is greater, but the other one is less than the negative. Okay, the negative a, the opposite of the number. Okay, so we can go in, again, we can go from up here, we can go in both directions. So the absolute value of u being greater than a translates, is equivalent to u less than negative a or u greater than a. And the same thing holds for greater than or equal to. The absolute value of the expression that includes x, u, greater than or equal to a, translates to or is equivalent to two inequalities. The u is less than or equal to negative a, or the u is greater than or equal to a. Let's look at an example. Always helps to clarify things. So here I have one. Solve the absolute value of 2x minus 5 is greater than 3, and graph the solution set. Okay? Okay, so we know, because it's greater than, there are two possibilities. Okay? Looking here, there are two possibilities. The one possibility says that what's inside, 2x minus 5, could be less than negative 3. What's inside is less than the opposite of the number. What's inside is less than the opposite of the number, or what's inside is greater than the number, or what's inside, 2x minus 5, is simply greater than 3. That tends to be the easier one to remember. So we have to solve two inequalities, but neither of them are compound inequalities. So we're back to where we want to be. Let's add 5 to both sides in this one. 2x is less than 2. Let's divide 2. Notice I'm not dividing by a negative. So there's no reason to reverse the inequality. X is less than 1. So I have x is less than 1. Okay, so that's going to go off to the left. And let's do the same thing in solving this inequality. Add 5 to both sides. 2x is greater than 3. Excuse me. 3 plus 5 is not 3. 2x is greater than 8. Divide both sides by 2. Again, I'm not dividing by a negative, so there's no need to reverse the inequality. And x is greater than 4. Okay, so I'm going to have two arrows because I had two separate intervals in my solution set. Okay, so my solution set. Okay, in set notation, all x's such that, well, x is less than 1 or x is greater than 4. There's my set notation. Let's look at interval notation. Interval notation, I have to have two intervals because they're separate. So one of them says, well, less than 1 means anything from negative infinity up to 1. So from negative infinity all the way to 1, and again, there's no equal sign, so with the 1, I'll use a parenthesis. This is everything less than 1. From negative infinity all the way up to 1. 0, negative 1, negative 2, negative 3, negative 4, all of those are less than 1. And then I'm going to combine that with, or union that, maybe you probably have seen some union and intersection stuff if you've done Venn diagrams, with this one. All x's greater than 4. So I start at 4, and I'm not equal to it, so I'll use a parenthesis. and I'm going to go all the way up to infinity, and of course infinity or negative infinity is always enclosed with a parenthesis, and that's how that one looks. Okay? So this is my set notation, this is my interval notation. Let's graph it. All right. I'll put my 0 here this time because I'm doing 1 and 4. Here's 1, here's 4. Okay. X is less than 1. Okay, I'm going to use a parenthesis to do less than 1. So there's my parenthesis. All these x's work. Okay. X is greater than 4. Okay, 4 is not included, so I'll use a parenthesis, not a bracket, and I will shade everything that is greater than 4. And so there's my solution set graphically on a number line. Okay, so focusing here again, let's take a look at the number of 2's we see, the things that are 2's in this. With greater than or equal to symbols, I have 2 separate intervals. You'll notice it winds up with 2 equations, okay, 2 separate solutions, and when I graph it, I'm shading 2 separate regions. Okay, all that's important to remember, kind of keep track of that. Now let's do this check graphically. So the left side, so graphically. Let's see here, I think I have enough space. I got 3 lines here. Graphically. Okay, I'm going to have y1 equal to the absolute value of 2x minus 5. I know that graphs as a v. I'm going to have y2 equal to the right side, which is just the 3. And I want the area, the plate, all those points. I want the interval of when y1 is greater than y2. So I want y1 greater than y2, as you see right here. Okay, so let's take a look. Okay, I need to go back and do some clearing. So back to y equals, let's clear these 2. Okay, y1 is the absolute value. Again, that's a math number function. There's absolute value. 2x minus 5. There's my y1. And again, if we graph that, we'll notice that graphs as a v. Okay, we knew that absolute value always graphs as a v. Let's go back to y and put y2 in being 3. We know that graphs as a horizontal line crossing the y-axis at 3. So the y-intercept is 3. Let's graph. There we have it. Now where is the v, which is the absolute value up here, above the 3? Well, it's above the 3 from 1 to the left and from 4 to the right. That's where the blue is above the red. I want to check the intersection points. Second calc intersect. Let's look at this side first. I'll pick, that's my line 1. Line 2, check. You can see here at 1 is where I would go from 1 to the left, but I know from this that 1 is not going to be included in my solution set because I don't have an equals here. Okay, now let's go back and check the other one. So second calc 5, and let's go over to where the other intersection point is. It's here. Enter, 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 and there's your 4. Okay, and from 4, starting at 4, going to the right, going this direction, the blue, which is the absolute value of 2x minus 5, is greater than, above, the red, which is 3. So there you have it. And again, we have our 4 right here. So there you go. That's absolute value inequalities. Okay, so let's recap briefly. With less than inequalities, we get 1 interval. We're going to get 1 inequality, and we're going to shade in 1 region. Okay, with less than or equal to. With greater than or equal to, we're going to get, let me get my paper up here, we're going to get 2 separate intervals. Okay, we're going to wind up with 2 inequalities to solve. They'll both be simple, neither of them is going to be compound, and we're going to wind up shading in 2 regions on our graph.